We're about to get started now on Kirchhoff's laws. For what it's worth, I have no German experience whatsoever, so I did look up in YouTube, how do I pronounce Kirchhoff? And here's my first few hits.
Kirchhoff, Kirchhoff,
Kirchhoff, Kirchhoff,
Kirchhoff, Kirchhoff,
Kirchhoff,
So the result is then,
Kirchhoff,
I just don't really know how to pronounce it. If any of you out there do speak German, please let me know, either on office hours or a little voice recording, because it is nice to say people's names right, even if they've been gone for a while. So I'm going to try and stick with Kirchhoff. Please forgive me if that's not right to those of you who are German speakers, and I will gladly fix myself if you just let me know how I'm supposed to pronounce it. So Kirchhoff's laws are really just the names of the principles we've already been talking about. Kirchhoff has two laws. There's the current law, sometimes called the junction law, and the potential law, sometimes called the loop law, and sometimes they're called rules instead of laws. So let's start with Kirchhoff's current law. So Kirchhoff's current law says that the amount of current into any junction is equal to the amount of current out of any junction. It's really just conservation of current. So let's say that I have a current I1 coming in to this junction right here where that T is formed. The net amount of current out is I2 and I3 added together. And they must be the same as I1. So at any junction, and most of our junctions are going to give a two-way split, but it doesn't have to. It could be a three or more way split. So at any junction, the net amount of current in equals the net amount of current out. It's a conservation of charge. So in terms of an equation, I1 is I2 plus I3. So there's our first law. The second law, the potential law or the loop law, says that for any closed loop, the net change in potential is equal to zero. So the total amount of potential when you add it up around a closed loop has got to be zero. So if I label the potential across any one of these devices, and we don't really know what these devices are, they're just kind of a mystery box, delta V1, delta V2, and delta V3, and delta V4 for the last one. So for any closed loop, the net change in potential has to be zero. In terms of an equation, delta V1 plus delta V2 plus delta V3 plus delta V4 equals zero for however many elements you have there. One thing, this might have popped into your mind, maybe not. Sometimes the potential difference can be positive and sometimes it can be negative. Some circuit elements will supply potential. Some circuit elements will use up potential. So we'll have to be really careful of those positive and negatives as we go through. We'll talk about that a little bit more on the next slide. If we talked about sometimes potential increases and sometimes potential decreases, how do we figure out which is which? How do we know where delta V is positive and how do we know where it's negative? So let's start a little bit straightforward with the circuit we have shown. We have a power supply, a battery. It supplies energy to a circuit, and we have it connected to a resistor. We know what happens inside the battery is that a charge is moved from the negative end towards the positive end by means of some chemical reaction. The potential energy of that charge is increased. The charge flows out of the battery and comes around the circuit. So the current comes out of the battery, flows around the circuit clockwise. continues through the circuit till it goes down and through the resistor. So the terminals of the battery are already labeled positive and negative. What about the resistor? Which end has high potential and which end has low potential? Well, we already discussed this when we talked about resistance. We know that current flows because of an electric field. There's an electric field established inside the resistor that makes the current flow through the resistor. And we know electric field points from high potential to low potential. So the top end of our resistor could be labeled positive and the bottom end could be labeled negative. So the positive and negative show that the positive end is just higher than the negative end. So then the current flows through the resistor, back around the circuit, and up into the battery. So if we label our terminals, that sometimes helps us figure out if potential is increasing or decreasing. So let's look at our circuit elements. We have the battery, and our battery supplies energy to a circuit. Oops, I left out my I from supplies. I don't want to leave it like that, so I'll just erase and fix it. So it supplies energy to the circuit by means of the chemical reaction within the battery. If it's supplying energy, the potential increases. So the potential and the potential energy of each of those charges increases as it moves from the negative towards the positive. If the potential increases through the battery, across the battery, then delta V of the battery, I'll put B for battery there, is greater than 0. It's positive because it gets bigger. Okay, our next circuit element is the resistor. Resistors dissipate energy. They use up energy. If you have a circuit connected, if you put your hand on a resistor, you'd see that it felt pretty warm. So resistors dissipate energy. If they're dissipating energy, if they're giving off energy, that means the potential and the potential energy decreases. If the potential energy decreases, delta V of the resistor has to be less than 0. Okay, and that matches our plus and minuses that we labeled on our diagram there. So if we wanted to write Kirchhoff's laws for our circuit, we would say delta V of the battery plus delta V of the resistor equals 0. And this even shows us that one of those potential differences has to be negative because we add a positive number to a negative to get a 0. Let's look at this equation in terms of our circuit diagram. So if we called the potential of the battery equal to epsilon, and we often do that, we would say epsilon, the potential of the battery, is equal to the change in potential of the resistor. From Ohm's law, we know that the change in potential across the resistor is going to be current times resistance. So epsilon, the potential of the battery, plus the potential of the resistor, which is negative because it's a drop, current times resistance, have got to be 0. So there's a very simple application of Kirchhoff's potential law. And we've added up that potential by going around our loop. So this is the loop that we added up the potential around. And this is the sort of application we're going to be doing. Now, we've talked a little bit about supplying energy and dissipating energy. When we talk about energy changing, we often care about what is the rate of energy change. And the rate of energy change is power. So power has a symbol of P and a unit of watts. It's change in energy, delta E, over change in time, delta T. The kind of energy change we get in circuits is change in potential energy. We remember that potential energy is however much charge flows times whatever potential it flows through. And if we look at our expression, we've got delta Q over delta T here. That's just equal to current. So the power of any circuit element is the current through it times the potential across it. Let's write down that result. Power equals I times V. I is in amps, V is in volts, and power is in watts for W. There's some things you can do with this expression. If we filled in that V equals IR, then we would see that our power is I times V, or I times IR, for I squared R. Another thing we could fill in would be that our current I is V divided by R. So V divided by R times V would give us V squared over R. So there's a couple of expressions that we can use when we're calculating the power of any circuit element.